We're about to start, and Atul and Moses will talk about mistakes we made integrating security scanning into CI/CD.
Hello, everyone. How are you all doing? Thanks for attending the talk, and thanks for organizers for having us here. My name is Atul. I work as a senior product security engineer at Box, and this is my first time at BSides. And I have Moses with me.
I'm a staff security engineer on the security automation team, also at Box. Not my first time at BSides, but I'm still excited to be here.
All right, so today we are going to talk about the mistakes that we made while integrating some of the scanners in CI/CD pipeline. So as someone said, that you don't live long enough to make all the mistakes by yourselves, so you have to learn from someone else's mistake, right? So you want to learn about the mistake that we made? Let's do it. All right, story time. So on one fine Monday morning, our product security Slack channel started showing up 100 plus different Slack messages from various developers, and they were complaining about their build pipeline getting failed. And the reason behind this was because one of our security scanner, it failed as the SSL certificate for that scanner got expired. Now, ideally, our configuration management tool should have renewed this SSL certificate, but for some reason it did not work. And we also did not realize about the SSL expiry. Now, even then, we should have avoided these incidents if we had designed a system that rolls out the scanners in a fail open mode. But unfortunately, we did not have that design in place at that time. Also, we could have narrowed down the overall incidence time window if we had put some good documentation on how to renew the certificate manually in the event of failure. But we had a blind faith in our configuration management tool, and we expected it to work all the time. So when the event occurred, we had to talk to our internal security team and get a new SSL certificate. Also reached out to vendor to see how exactly we can roll out this certificate on the scanner. So overall, between like 7 to 8 hours, our developers could not push any code whatsoever to the production. So any incidence is basically a chain of events. An event cannot occur has a capability to cause an incidence by itself. So all the events would work together to make an incidence. Now, so before we go and show you the difference between our old model strategy of rolling out scanners to our new model and compare them both, just to set a stage for everyone, let's quickly walk through the DevOps methodology. So DevOps is not a tool. DevOps is basically a software development methodology, which is adopted by development and operations team. So in any organization, you basically have these two teams. One is development team, and the other one is the operations team. Development team would write a code and give it to the operations. Operations would then test the code, build the code, and deploy it. Now, in ideal world, there shouldn't be any confusion, any issues, but these two teams always have a conflict of interest. So the tool the code that works on development team's machine may not always work on the operations team machines. Also, the goals for these two teams are totally different. Developers want to release the code ASAP, so agility is their goal. Whereas the operations teams, they want the stability. They don't want to break the system. And in order to establish a good collaboration between these two teams, that led to a creation of a methodology called DevOps. So one thing is missing in this whole DevOps cycle. Anyone knows what it is? Any guess? Obviously, this is a security conference. That's why we are here, right? So security can be added at multiple different layers in this DevOps cycle. So we could train the developers on how to securely write a code. We could have a pre-commit hook to detect the code vulnerabilities right when the developer is writing a code. We could even have a DAS scanner or a SAS scanner detecting vulnerabilities in runtime. So in this topic, or for this discussion, we're going to restrict our discussion to the CI security. All right. So let's quickly go through how exactly this overall DevOps cycle works. So a developer would commit a code to a version control system, and this version control system could be a GitHub, Bitbucket, or any other software. If there is any change detected in version control system, it would be picked up by CI and CD softwares. And then they will deploy this code to a testing environment or the test server. On the test server, you will have a bunch of different softwares like Selenium, which would have different test cases that would run against a particular code. Let's say for some reason one particular test case failed, it would error back to the developer, and then developer has to fix that code and make the changes, and the whole cycle will repeat. Now, let's say if you're lucky, there are no test cases that fail, everything passed, then you would push that code to the production. So that's the basic understanding or very high level overview of how DevOps works. And when security becomes an integral part of the DevOps, it's called SecDevOps or DevSecOps. So let's take a look at how exactly we added security in CI tool. So we are using Jenkins as our CI tool. And as you see on the screen, we have a Jenkins file, which is basically a text file that defines different stages that goes or runs as a part of the Jenkins pipeline. So these stages could be prepare or build, test, deploy. And in this case, we have added a stage called security. As a part of this stage, we would invoke multiple different scanners. As you can see on the screen, we are invoking tool 1, then tool 2, and then tool 3. If we expand the definition of, let's say, tool 1 in this case, you would see OWASP dependency check scanner being invoked, which is again an open source third-party library, and that would find the issues related to a third-party library. And if you just take a look at the parameter that we pass to this ODC or OWASP dependency check scanner, one of the parameter to notice or is critical is the fail on CVSS. So fail on CVSS basically breaks the build if there is any vulnerability with a CVSS score higher than the predefined level identified. We'll come to this particular parameter in a moment. All right. So in ideal world, everything should work without any failure. But if issues like SSL certificate happens, then this system won't work. Other than that, we have also observed a couple of challenges with this model. The very first challenge is having no standard way of invocating these tools. If you're a Java or a Scala developer, you would always look for a Gradle plugin for the tools. Also, you can containerize these scanners. You can have a shell script, like we saw on the earlier slide, that you can invoke a shell script, and that would eventually invoke a scanner. So initially, when we were rolling out this model, we were pretty flexible with developer's choice because we wanted to keep them happy. But eventually, that increases the workload for us because now we have to maintain different ways of invocating scanners. Also, this model did not have a global switch. So for example, if any tool stopped working for any reason, then we don't have a way to disable that tool. It also means that if, let's say, this tool is deployed to hundreds of pipelines, then we have to make developer create hundreds of pull requests. Not an ideal case. Then we don't have a central management. The previous parameter that we talked about was a fail on CVSS, which is a very critical. And we want product security team to have a control of that parameter. We don't want developer to have the control of that parameter because they might just tweak the parameter, they might update it, or they might set it to a value that won't fail the build. Then the fourth challenge was having no metadata whatsoever. So we don't know which particular pipeline invoke what tool, how much time a tool take, and what's the performance. Then the fifth challenge was having no error log. We don't want to hear about the complaints from the developers. If there is any error, we want to be notified ASAP and then act on it. And last but not the least, and very important, is having no sleep. Product security team had to be on toes and with fingers crossed all the time and hope that all these tools will work. But unfortunately, that's not the truth. So I'll hand it over to Moses now, and he will walk us through how exactly we solve all these problems with a new model.
Thank you. So that's pretty much it for mistakes. Next, we want to talk about how we solved these problems. So I'm not aware of any product we could have bought that would have just solved this. So we went right away to building something that was going to work for us, address all of those issues that Atul just raised, and above all, ensure that we never break the build on accident again. Now, oh, by the way, we don't have the slides uploaded yet, but we'll get them up right after this talk for everyone taking pictures. So the things that were kind of at the top of our mind, the principles that we needed to address and build in from the start, well, were up on the screen. We'll start with fail open. So after we accidentally broke a bunch of builds, that had to be top priority. We can never break things on accident again. We should handle errors. We should let builds proceed if one of our scanners throws an error. We need it to be usable. Whatever we build, it's got to be easy for our team to maintain, and it's also got to be easy for developers to put into their pipeline code, or their build pipelines. It's also got to be scalable, which doesn't mean that we need to be able to scale to exabyte scale or anything. We're not really dealing with data processing here. Rather, we need it to be scalable organizationally. We need this to be something that can be rolled out across the organization. We want this to be in every single build pipeline, ideally. With that kind of scale, we need it to be efficient. And again, I'm not talking about being algorithmically optimal, just that it can't really slow down the build. Relative to total build times, our security checks should be quick and not add a lot of overhead. We want everything to be observable. Like Atul was saying, we need error logging, we need error alerting, because we don't want our users to have to report that something broke to us. We want to get the error, be notified right away that something happened. And we want to manage everything centrally. So if we want to switch to a new scanner or update something in a scanner, we want to do it in one place and have that reflected across every pipeline that's going to run these scans. So there is a famous quote attributed to David Wheeler, sometimes called the fundamental theorem of software engineering, that any problem can be solved by adding another level of indirection. So that's what we did. We decided what we need to do is build a library that just abstracts all of that code to run individual scanners into our own library, and then push this out so that to integrate this into someone else's pipeline, all they have to do is import our library and run this run security checks function somewhere in there. And that'll just be our entry point to kick off whatever code we want to add. Now, we did this in Jenkins, as a Jenkins shared library. That's what we use, so it's kind of how we had to do this, which has some interesting side effects. We had to write it in a language called Groovy. I'll get into that later. But at a top level, this is what it looks like. All we have to do to get this imported into a pipeline is import it with that @library syntax, and then add a stage to the pipeline that just runs that one function. We did add another nod to fail open and to making sure everyone's confident we'll never break anything by also adding an option to override the checks without disabling it, so it's not commenting it out, but if you pass that emergency override equals true option, the whole thing just logs that it happened, and we let the build proceed. So at the implementation level, how this works in Jenkins is that you set up your shared library through the configuration by telling Jenkins, hey, here's a GitHub repo. I want to call this security checks library. And that then makes it available for importing in any pipeline running on Jenkins. Then we have that run security checks call, which is just going to call one of the functions that's inside our repo. So that repo has a couple big components, and I'll go through each of these in more detail. But basically, we've got a file we called config.json that says what scanners we want to run for each repo. And we've got a bunch of scripts to run each of those scanners, similar to the one that we saw before for the OWASP dependency check. So once our code is called, what we do is we just parse that config file, and then for each scanner that we get out of it, we write that scanner script to the directory, we execute it, we do whatever we need to with the scan results, and then we delete the script and leave the build environment like we found it. Here's that config.json file. We knew we needed something that was going to be flexible and could be changed per repo or even per team or GitHub organization. So we set it up with this hierarchy where we define scanners for the baseline. These get applied everywhere. And then we can layer on top of that rules for an organization. So for the security org here, we also enable other scanner. And then we can go down to the individual repo level. And here we're actually disabling some scanner. So in this example, we're only going to run other scanner on security/some repo. And yet another nod to we will never break a build on accident, and this can be disabled if needed. We have this disable checks flag that will turn everything off if ever needed. In our actual run security checks code, again, this is in Groovy, but we can follow the logic pretty easily without worrying about language details. You can see we implement this call function that's going to get invoked. We print a couple things that'll show up in the build pipeline log, let everyone know where to go if there's problems. And then we wrap everything in a try-catch block. This ensures that if there's any error anywhere in our code, we'll catch that error, we will write it to a log, and then we will just silently fail and let the build continue. Assuming we don't run into errors, we just go and parse that config.json file, get the list of scanners. This is going to be just a list of strings, the names of the scanners. Then for each one of those scanners, we're going to go execute the Groovy function that implements that scanner. I'll get into that in a second, but then we grab the result, we log that, and we're pretty much done at that point. Now, I mentioned Groovy a couple times. I don't actually know Groovy, and I wrote this thing. Does anyone here know Groovy? Yeah? So we couldn't have this be a Groovy-heavy project, or no one in our security team would be able to update this tool or fix things. We would have a really hard time integrating new scanners, because who wants to learn another new JVM-based language? It's actually got some cool language features, but I won't even go there. We didn't want to learn it. So we adopted a model of using Groovy to kind of glue together the pieces of our code, and this is what we had to do to get it implemented as a Jenkins shared library. But all of our logic is implemented in Python scripts and Bash scripts. We just have Groovy run them with something like this runshell.groovy function, grab the result, and return it back. One of the nice things about this is that it means we could rewrite this library to run in some other build system pretty easily. We just have to replace that glue code, but all of our logic can be the same. We can still use the same config.json file. So to add a scanner in this example, we have to have one Groovy file that we add to the repo. That's going to be named here examplescan.groovy, but all that's going to do is call that run shell function that we just saw on the last slide. That'll grab the script out of our resources directory, write it into the environment, execute it, return the value, and delete that file. Now, you can put a little bit more stuff in there. It's a really convenient place to grab secrets out of the Jenkins secret store, if that's helpful, but you don't need it. Like that's the only Groovy you actually have to write to add new things to the scanner. Then we've got a shell script that we actually execute the scanner with. One of the really common patterns is to just have that shell script pull in a Docker image and run that in the build pipeline. That helps a lot with reproducibility, because Jenkins does not make for very reproducible builds as it happens. But so it's yet another layer of abstraction that we kind of bolt on. And then to enable this scanner, to have it actually run on a repo, we just add the name of that scanner, the name of that .groovy file, somewhere in config.json. So for development, we would add this to some test repo, and then we'd go push a build, see how it runs. Then we could move it into the baseline and apply it everywhere in our config file. So all that is pretty lightweight and not a lot of tooling around it. But one of the things that we talked about that we really needed is logging and alerting and metrics. Now, if we were building this as like a product that we were going to try to sell to other companies, we would have had to go for some kind of a really heavyweight solution where we have a way to aggregate logs ourselves. Fortunately, we're not building a product. We're not selling this. We're building a solution for our specific environment, which is a much more tractable problem. And we took advantage of the fact that we've already got Splunk running on every system, picking up logs, forwarding them to a central location from which we can build dashboards and alerting. So that's what we do. Everywhere we write logs, we're actually just writing to something like var log securitychecks.log. And then that's it for the library side. Then we went to Splunk and we built up dashboards. We built up alerts that will create tickets or Slack us when there are errors. And we've got all these nice metrics. We've got graphs, makes management very happy. It also tells a really nice story about adoption of this library. We can show how many repos have adopted it, how many scans have been run. It really makes for a pretty compelling story showing how our scanners are hopefully adding security to the organization. So right now, that's pretty much what we're running. We never break a build, ever, even if there are vulnerabilities at the moment. But we do want to be able to break builds based on critical vulnerabilities. So we are working right now on adding that functionality. part of the requirements before you build something like that is that you have to be able to manage false positives, whitelisting, things like that. So for that component, we're actually building out a workflow where we create a ticket in our ticketing system for each vulnerability. And then in order to whitelist it, we have a workflow built on the ticketing system side where you can set it to be a false positive that gets reviewed and approved. Once the ticket moves to that state, we automatically call our scanner API and whitelist that vulnerability. And then closely related with that, we're going to pull all of those tickets, all of those vulnerability scan results into a panel inside the Jenkins build so that when you actually run security checks library in your build, it can show you every scanner that ran, what the results were, and if we broke the build, it'll tell you why right there where you actually need the information. This will simplify things a lot. And it's a lot better than the situation where you have to train your developers that they have to go find a particular file that we wrote out somewhere with scan results. Or worse, have them go log into a scanner server somewhere to get the results for their scan. So there are a couple of takeaways that I hope people leave with. I feel like almost nothing I've talked about here is very hard to implement programmatically. I think it's really more of a pattern, something that's pretty straightforward to do, to add a layer of abstraction to run security checks in a standardized way inside build pipelines. Now, centralizing how you run security scans is very important because you will run into a lot of cases like we did where something changes, something breaks, and it breaks every pipeline. Another example that we might have run into recently was that we needed to update a database, and pushing out that change to every single build pipeline that uses that scanner would have been a really big problem. So we're actually migrating all of our scans to use security checks library. It's really important to have everything centralized. And to reiterate, this isn't tied to Jenkins. It's not tied to any of these languages. You could implement this at a really simple level just by having your code in a Git repo and containing some shell scripts, and have your instructions for integrating into build pipelines to be clone the repo and run a single shell script. That gives you that entry point to run arbitrary code inside a build pipeline. And from there, you can do anything you want. We can use this logic, or we could even kick off some other tool that we use for scanning, for deciding what scanners to run. So that is our talk. I want to quickly thank Dinesh, whose name is on the talk but couldn't be up here due to a change in employment situation. Thank you, everyone, for your attention. I think we've got a couple minutes left, 1 minute left, so we'll be happy to take any questions we can fit in there. Someone here?
First of all, thank you for the great presentation. I have been dealing with this problem for a number of years, working with developers who want to integrate CI/CD security tools into their CI/CD. So this is definitely something that a lot of people encounter, and that's quite useful. Have you guys heard of Salus? It's an open source framework.
Yes, we have heard of it, and we didn't opt to use it, but basically I think it could have been integrated into our system in place of the code where we actually go and run the scripts. Like, we could keep everything the same, our logging, the way we get it into libraries, and we could just invoke Salus to do the script running.
Right, yeah, that's what I was wondering, because I've built something very similar. We're using Salus. I wondered why you guys went in this direction rather than using that.
We weren't familiar with Salus when we started building it. Once we were familiar with it, I kind of said, I'd rather write it in Python.
Awesome.
That's about it.
Great work, thank you.
We also have a Slido question, if we could answer that.
Sure.
Let me just read it out. You have baseline policies and policies that are org repo specific. How have you organized app code in these repos? What's an example of an additional policy?
Yeah, so right now we don't have a baseline policy, but there is a scope for adding that as a parameter as a part of the config.json. So this work is still in progress, so we would have much more development in future. including the policies.
All right, thank you. One more question? Okay, last question.
Then we'll be out in the hall for a while as long as anyone wants to talk after this.
I was just wondering if you had shared any of this code on GitHub, in your GitHub, or any of it's been kind of
So
more concrete examples?
We haven't actually shared the code yet. We do want to release it open source, but haven't managed to push it all the way out yet. We're kind of trying to, I think it's a pattern, and hopefully just talking about that is helpful. But we do want to get our code out there, see if anyone else can use it. So that's on the roadmap. I'm sorry it's not done yet.
All right, thank you. Thank you for...
Thanks, everyone.